All right, here we are in Unit 3, Part 1, Newton's Laws. This is video 2, discussing in the free body diagrams. This one will partake more on the examples of how to draw them out. So let's get started. First thing we'll want to do is make sure that we still remember what these symbols are. And how we will be using them as we move forward with it. So if you didn't write it down from video part 1, feel free to write them down now. Make sure that you have, again, all of the parts that you need. The force, the symbol, the definition, and the direction. Here's this was the last slide on the previous video, in that it had all of the different things that we're going to be talking about. One of the first things that we would need to identify is the system, and that Dexter is the system here, and that he might be standing on something. We don't know what. Would it be the ground or whatever it is, but that's not really the worry. Things that we can identify here that are going to be important: that Dexter is has a weight. He has a normal force of the floor pushing back. It should be at the same exact arrow size. There is a push on him of some sort and a frictional force of some sort. That's how we're able to identify that. Now, would all those be happening at the same time to Dexter? Probably not, but it just it's an example of what these potentially could look like. So, kind of a step-by-step process with these is, for one object, draw a free body diagram showing all the forces acting on it. You try to make the magnitudes and the directions as accurate as you can. Again, one of the key things that we've always talked about is, when in doubt, draw it out. Free body diagrams are getting into that same idea of, I don't know if this object is moving or not, or what if all the forces are balanced. Well, when in doubt, draw it out. And so then we're going to label each force. If there are multiple objects, we draw separate ones, and that one's going to be a little bit trickier because you have to look at things a little bit differently. So resolve the vectors in their components, meaning if it's ups and downs, lefts and rights, and then see what you have there, and then apply any Newton's laws that are there. So therefore, we are going to start with free body diagrams very simply in Newton's first law, just to see if they're balanced. Newton's second law, we're going to see if they're not balanced. Where is it moving to? How is that causing it to move? And in part 3, when we talk about Newton's third law, we will actually talk about what's called third law pairs. So we'll just kind of build on this as we continue on. So again, starting simple, and then we will build on it as we continue. So first one that we have here, some things that are very important, helpful, is when we identify the forces, that it's A on B and B on A. And so that's going to be something that we'll try to start now at the beginning, so that when we get into talking about Newton's third laws and Newton's third law pairs, we don't have to add an additional part to it. It's just kind of making use of it. And I prefer, there are other routes to take with this, but I prefer to use the what on what. This was done, A is on B, force A on B, force B on A, depending on what you're dealing with. That's my preference, and it's in the majority. I have seen a couple other ones that just does add some confusion. So this is the what we're going to go with, and we're going to see where those interactions are happening. It doesn't always happen, but sometimes they do. So let's think about this. Two forces acting on a book or resting on a table. Its weight and its support force from the table. Does a force of friction act as well? Well, we're going to think about this here, and by thinking about that, we will again draw it out a little bit. So we have an object, two forces acting on a book. So we're just going to draw a very rudimentary table, and say that a book, and I'm just going to draw a rectangle for the book, is resting on it. We know, maybe I'll color it in a little bit there so we can kind of see some things. It's a book. And so now we know that there are forces acting on it. We know that there's the weight of gravity on the book. And then we also know that there is a normal force and that would be table on the book. And that's usually how we indicate that. So two forces acting on a book resting on a table, the support force and that. Now, ideally we would say, okay, does the force of friction act on it as well? Well, friction is the opposing of other motions, and so since there is no movement left or right, we don't really need to worry about them at all. And so therefore we could say, no, I don't think I need to draw friction if friction isn't present. Because then we would have to draw something to counterbalance it, because if the object isn't moving, that's the only forces that would be present and how they would look. Now I can draw this out a little bit differently. And so we can even go simpler. And some of you might enjoy or like this a little bit better, in that we just worry and literally draw what's going on, and that's where labeling things is so important with this. And so it can eliminate some of the other parts to it, and we can see, oh look, these two forces are equal to each other, and therefore they're going to equal 0. No Newton, 0 newtons is going to be there, so because they equal out. And so therefore we know no motion is happening. Now let's look at a little bit more of a complex situation. What we're looking at here, we're only going to worry about that as the whole system. Okay. We will also look at each individual book as a system as well. So because that can be extremely complicated, we're going to just make it, let's make it simple for ourselves. Let's do the green book first. And so let's draw that out. What is that going to look like? Well, I have the weight of the green book from gravity, but then I also have a normal force moving up from the blue book on the green book. Now that we have that one, we can look at the next book, and that would be the blue book. And I'll draw that one off to another side here. Color it in a little bit so that we can identify the blue book. Now the blue book has a couple different things. The blue book has the weight of it with gravity. Now it also has the green book pushing down on it, and that would be the normal force of the green book on blue, since we're talking about the blue book. So everything is going to be on blue. Okay. Now also, ideally, those two forces should be equal. Arrows should be the same if I did this correctly. Now, because the object isn't moving, the arrow that I draw up should equal the sum of the bottom two arrows. And I'm going to try to draw that the best that I can, as we have there. And that would be labeled as the normal force of the red book on the blue book, since we are again talking about the blue book. So again, this arrow here should be the sum of the weight of gravity, and it should even be on blue, plus the sum of the green book and blue book, but it also in the opposite direction. So that's where you would have that, because there's no movement. Now the red book is going to have even more arrows, or some would think, but it's not going to look too much different than the blue book. Now, one of the things a lot of people think is that the green book is going to be on the red book, but the green book is not on the red book. The green book is on the blue book, which is then on the red book. So here we don't have the normal force of the green on the blue. Here we have the blue on the red, since we're talking about the red book again. Now, these again should be equal if we did everything right, if we drew it out right. And that's again based on what I look at. And so when we have, then again, going under the impression that all of the weights, I'll change my color here, all of the weights of the books are the same, and therefore the colors, the arrows or sizes are going to be about the same, and that would be again the weight of gravity, or some would say weight of Earth on the object would be another way of looking at it. And so it would be on the red book, again, because we're talking about the red book. Now, the up arrow, the normal arrow of the tabletop should be the sum of these two forces again, but in the opposite direction. Okay, so what I draw up here should be again the sum of those two forces, but in the opposite direction. And that's again drawing it out best that I can that we have. And so we would have a normal force of the table on the red book. We don't draw anything out for the table because that's not anything more than just holding the books up. And so here we have all of that. Now we can draw all of this out as one big thing, as one big system as well. And what that would look like is we would draw a bigger box to kind of indicate all of them, the normal force of moving up, and then the weight of them all being down. And so we would have kind of the summing of all of these individual books being put together. So we would actually have to find the weight of the books, and that would be the sum of all the forces, and that would be the weight of gravity on the green book, weight of gravity on the blue book, weight of gravity on the red book. We would add all of those up to give us the weight of all the books stacked. Then we would have to then add up, and here's the thing, is actually the weight or the normal force will be equivalent to the normal force of the table on all of the books, or actually it should be the same as the same normal force on the table to the red book, because it's on the bottom. So that's one way to also look at it. So when we have tension, that usually means that there's a rope or something in that. And so we have to be careful, because tension can become very complicated, and again, identifying our systems. So here, again, we're only looking at what is inside the circle as our system. So there's going to be the force of gravity down on the bucket, well, whatever's inside the bucket. Then there's going to be a tension force moving up. Now, we also should know that there is those two forces should be opposite, because usually it's going to be attached to something, or something is going to be pulling on it, and so you're going to have that equaling of forces, and so it's going to still be there. And those would be what we call Newton's third law pairs, okay, because they kind of interact with each other. Those are interaction type things, and so we have that part. And so we have to be careful on how that works, but that's what it kind of would look like. And again, identifying what's in our system is going to help us out and understand that. So when these forces are unbalanced, such as a hockey puck is at rest, and somebody hits it, now all for a very short amount of time, when that object hits the hockey puck, it is interacting with it and it starts moving down. Now there is also a resistance to it moving down the ice. We use a hockey puck on ice because there's not a lot of resistance, but there is some. But there is a large unbalancing of forces. But once that puck starts sliding down the ice, we can see that eventually it does slow down just a little bit. So the frictional force then starts kind of there now until somebody hits it again. Then you start seeing something more, and that actually will start bringing up the why is it moving in this direction, and that's Newton's second law stuff that we will start talking about actually soon after we take our test covering Newton's first law. So kind of where that draws and where we're taking this is all understanding that, and we will even draw free body diagrams as we look at these different ideas, is when it's at rest, when it's hit, and then looking at what happens as it's going down the other, and then if it were to get hit again, how would that change the direction and how that looks. So those are some things is that you can kind of see in a step-by-step picture, kind of like what's changing in the picture, which means what's changing to the object as well. It would be like they would use it as storyboards for movies. It's kind of like what is the big scene, kind of laying it all out before they kind of get into and dive down into the nuts and bolts of the scene in the movie. So it's just another way of looking at it in ways in physics. So again, hopefully this helps out and explain of the how we draw these out and continue to move forward in our curriculum.